Thank you all for coming. My name's Kane. I'm a grad student at the ESCI program. And today we have Temur Akhmedov. He's from Bourne Energy Engineering, basically a firm that works with designing and implementing energy efficiency practices. He's going to be talking to us today about the future of buildings and how energy efficiency and renewable energy resources are going to be play a major role in that. So you can give a round of applause.
First of all, I want to thank you, Dr. Shankar, for having me here, and appreciate the opportunity to share my thoughts and ideas on a little bit of the experiences I was discussing a little bit earlier. This is always a little bit of experiment, the presentations, as I take content from previous different presentations, add some new ideas, and depending on the audience, we'll try to mash things up a little bit. And it actually becomes, when we have a crowd like that, when we have students, graduate students, and faculty, how to present the ideas so that they make sense, they're relevant. That's always a challenge, which is exciting, which is very interesting for me. The subject here is pretty broad, and I intentionally kind of left it broad like that. I know that the most of the series is related to the generation side, the utility side. So this seminar is more related to the usage side. We can say it like on the other side of the meter. So if you take a meter, on one side you have utilities with all the transmission and everything, and on the other side of the meter you have buildings, you have consumers of the energy. So this will be more related to that component of the equation. And on energy efficiency and renewable energy, people have all sorts of ideas. They have personal beliefs, sometimes very strong beliefs, and this subject obviously is very political, whether it has to be or doesn't have to be political. But today we will not touch the political side of it. We're just going to look at the technology, at the merits and the trends, and where things are going, and whether it even makes sense for us to look at these things as a component of the broader system. So before I start there, what I like to do usually is to show you a little bit. Hopefully the volume is. Want to start the presentation with you falling face down. We made a little change there. But the reason I use this video, because as I was saying, people have those conceptions, have ideas, and it's always a challenge just to have a seemingly simple discussion on these matters. So I want to, obviously you cannot kind of set aside your beliefs and your understanding, but I want to keep sort of this free discussion. And as we go through this, first of all, I will be asking questions. And second, I'm more than welcome the comments as you go through. If you have any questions, you ask them, because this will be more of a discussion rather than just simply presentation. I don't like to stand and just talk because I don't think that would make much sense. So before I launch into the whole event, I just want to make sure to share with you, I guess, why am I standing here? The Bourne Energy Engineering has been around for almost 20 years. and focus on energy efficiency. Bulk of the work, what you may not have heard of the company, even though we have an established name, we work for utilities. Bulk of the work is on the utility side. So when utility companies have incentives programs, for example, for energy efficiency improvements, there's usually a third party involved that verifies that improvements were carried out, that the savings took place, and we review the measurements, we review the calculations, and tell utility, yes, it's okay, or no, it's not okay. And we work for all the major utilities in the region. And working like that gives a very comprehensive view of buildings, from how they use energy, how they purchase energy sometimes, and how the occupants use energy. So it gives a little bit broader picture, and it challenges, especially on the engineering side, thinking how all of this, how it's supposed to work together. So I'm going to start with a chart that I'm sure you have seen many times, right? So typically, these energy food chain, I guess, is brought up to show how, taking a coal-fired power plant as an example here, you have the flow of energy with the losses and the usage throughout the process. So you start off with 100 units over here, coal-fired power plant loses a whole bunch of energy, so you only have 62 units going into the grid. There's a little bit of loss through the infrastructure here, and then you end up with 36 units at the building level. Now, this is moving away, incandescent bulb, although I do know people who stockpiled incandescent bulbs before they were taken out of the market. But if you look at the incandescent bulb, probably about 3% energy of incandescent bulb actually goes towards light. The rest is heat and other losses. So this is typically how discussion goes. You saw how, look, we have these losses, this is all we're getting. On energy efficiency side, what I try to do actually flip the conversation here. So instead of going this way, let's go this way. So what happens if we turn off this light bulb?
Don't consume 36 energy.
You don't consume 36, and if you keep going down the chain there, this is a number, right? So the 100 units is the one that you don't need. This is the impact of energy efficiency sort of on overall grid, on overall sort of the utility scale. So you're not using on this end, therefore there is no need for that. Now this is obviously, that's simplified view of it. It's not necessarily exactly that way. The coal-fired power plant works 24/7, regardless of what happens, and the utilities manage multiple ways of generating energy. So it's not exactly working the way that you turn it off and it's automatically less energy over here. But the basic premise is that if you're not using on this end, then this whole chain, there's no need for energy to flow through the whole chain to get you over here. All right, so what we would like to do, as I mentioned in the premise of this, in the abstract of this for this seminar, is that we want to look at how buildings are constructed and what has been the quote-unquote tradition and what the new stuff happened, to see where the efficiencies are, what actually makes sense. So what I like to do usually is to look at the history of how buildings were constructed. So if you look for thousands of years how buildings were built, primarily homes but then larger buildings as well, they try to take advantage of local environment. So you have here a grapevine growing over that provides shade over the area over here, and there's actually goes over the house, so it provides shade for the house. So it keeps the house cooler in summer. And it's also, obviously, you can harvest grapes here, right? This is an example of a house in Central Asia, for example. or many of you, I'm sure, have seen adobe homes, right? Very suitable for dry desert climate. Probably not very suitable for the Northeast over here with the humidity and rains. But there, this is just fine. This is what allows the people inside the house to stay relatively cool at the peak of the heat and stay relatively warm at night. Then you look at a log house. This is more our Northeast area, right? Where, again, using local materials, suitable for local climate, managing humidity, managing heat loss, and all of those components. So if you look throughout the world, you will see that what happens is that there is use of locally sourced materials to build the buildings, which is, in most cases, you don't have a choice. If you look sort of historically, you're not going to drag stones, you know, for hundreds of miles to build some buildings. You know, if it's not like a pyramid or something. But for homes, you use local materials. The construction techniques usually are suitable for local climates. So you design a building that fits, that provides you with comfort, safety, air quality, and all that stuff within that environment. Now, if you look at the sort of length of history, obviously there were mistakes made. This is how the learning happened, not necessarily through research, but through mistakes. And people learn through mistakes what makes sense, what doesn't make sense, what creates problems, what doesn't create problems. So it was actually a matter of survival. If you don't build the right structure that fits the right environment, you will probably die of exhaustion, overheating, being cold, whatever. And the house, if the house is not suitable, you will just not survive. And there are plenty of examples of that as well. Sort of on the broader scale, for example, when Vikings landed in Greenland, they did not survive there. They didn't adjust their living standards or the dwellings, the food chain, everything. They didn't adjust to the local environment, and they left and they died out. Buildings provided comfort, safety, and functionality. That was the sort of the main thing. I don't know how comfortable, obviously, some of the, 500 years ago, 1,000 years ago, the buildings were, but obviously people survived, so there was probably some level of comfort. I've been in homes, I mean, here in the Northeast, you have homes that a couple hundred years old sometimes, and I actually myself come from Central Asia, from Uzbekistan, so I've been in homes that were 120, 150 years old. And when it's 100 degrees outside, you walk into that building, to the house, and it's cool. It's because how it's designed, how it manages the overall energy flow. Many old buildings obviously still stand after hundreds of years. And while the use may change, the technology may be added, the core essence of the building is still solid. And that kind of goes to overall structure. There's a reason I'm mentioning all this stuff. As we go through, you will see how things are connected. For example, not related exactly to buildings, but the example that I like to use is the medieval bridges in Europe. They were built hundreds of years ago, but in the Second World War, they were able to handle 40, 50, 60-ton tanks. So some would call it over-engineered bridge. But from the other perspective, this is a sustainable long-term structure that can fulfill many functions over the years. So all of these components that I'm talking about, these are components of what the term that's currently used, passive efficiencies. These are sort of built-in components of a building. This is what makes the building efficient by itself without the need of technology. Because we didn't have technology up until very recently. So the buildings were supposed to provide ventilation, they were supposed to provide daylighting, they were supposed to provide warmth and coolness without the technology. All right, so now we're gonna move into the Industrial Revolution, the last 150 years, how things started changing, and that's gonna impact everything how we do now, right? So there was introduction of steel and concrete. Now concrete was known for a while, but it became like a mass material that was used for construction of buildings all over, right? And with the steel and concrete, you can build any type of structure you want, any size, any shape, lots of possibilities. So that gives you some flexibility. It also removes some constraints if you think about local materials like Adobe building. Obviously, you cannot build Adobe skyscraper. The introduction of electricity and light bulb. Now, once electricity became available, you were able to ventilate the space, so you don't necessarily have to provide natural ventilation anymore, right? You can design a building in whatever weird shape that you feel like designing it, and then put some equipment there to circulate the air, right? And with light bulb, now you don't even care about the daylight. You can put the lights wherever you want, and so the building can be a box. I'm sure you've seen schools, for example, some middle schools with almost no windows, right? And for me, it looks a little bit weird because how could you have a school with no windows? But we have equipment that can provide the light. It's not the same as we're understanding slowly. Gradually, we're coming to that saying that it's not the same. But that enabled those kind of changes. Then the sort of the final nail was HVAC system. Heating, ventilation, and air conditioning. Now, once that became available, you can build whatever structure, wherever, and then you provide. And if your building is losing heat or losing cool air, you just put a bigger system, and that was usually a solution, right? If you look at let's say homes for last 30 years, if you ask any builder, by default, their engineers may say, here's the size of equipment that you need to put. They will size it up a little bit, partially to make more money, but also to blow a whole bunch of cold air, a bunch of hot air, to offset whatever losses that exist in the building. So electricity is cheap, but then equipment is there. You can just put bigger equipment and you'll be fine. So that pretty much killed the need for efficient design. So if you look at buildings, at these homes like I was talking about, that over the last 30 years, if you cut the power, most of those buildings will not be able to survive on their own. Like if you take a building that was built like in medieval times, for example, or even most buildings built before electricity, if you cut the cord, it can stand. It will survive on its own, like without human occupancy there. But most of the buildings now, they cannot, those homes, for example, they cannot ventilate themselves. They build up temperature very quickly, and then with heat and humidity, you're going to have mold, and the house will be destroyed in no time. So passive efficiency is not built into those buildings. This is what we lost over the last 150 years. So with all the advances in healthcare and technological advances, we had an explosive growth in population, right? People didn't die as fast, they still made babies, so the population grew. And with that, obviously, you had growth in consumption. Explosive growth in consumption. Supposedly, I mean, the life comforts, I guess, the quality of life is better now than it was 150 years ago for vast majority of people, even though I'm sure in some parts of the world people may object to that kind of description. But the idea is that we need all this stuff, right? So we need to consume more. That whole logic about putting larger equipment, putting more light bulbs, this is all interconnected. How we do that? So the big question here, are we really consuming all this? Not really, right? We're not really consuming all this. So the reason I'm bringing all this up is that there's a fundamental idea that at the core of energy efficiency that I think helps people better understand what it is and why you even need to deal with energy efficiency and how it's related. So the fundamental issue is the difference between use and waste. So, question to everyone. What is use?
That which we actually consume.
Okay. An example.
If I buy a dozen eggs and I eat them all, then I have used it as opposed to letting them go bad and throwing them out.
And throw them away, okay. Any other explanations for the use? No?
Packing materials?
I'm sorry?
Packing materials?
Packing materials. Is it a use or is it a waste?
Protects goods on the way, but then what do you do?
Right. So it serves certain function. I remember they cut down those little flash drives. Used to have these massive plastic boxes around. They're a whole lot smaller now. But when I talk to people, they would explain that this is to protect from theft. So you don't carry this whole thing. So there's function there. But like you're saying, can that goal be achieved through some other means? And what happens with that boxing, with that packaging after something is used? So, and how do you, so in this example as we're talking, like using the eggs example, you used the eggs, every one of them, great, fantastic, you didn't waste any of the eggs. But there was packaging that those eggs came with, right? What happened with that packaging?
Tossed.
Tossed. Right? If there's a possibility for recycling, you would recycle it and hopefully it will go back into the whole concept. So, but there was a use for that packaging, because otherwise you wouldn't be able to bring those eggs home, right? So this is what we're looking for here. The core of this is a benefit. We seek benefits. We don't necessarily need to use energy. You don't care about the electricity. You don't need electricity. You don't have any way of using electricity like on your own. What we need lights, right? We need cool air. We don't need how these lights are brought in is almost irrelevant. Yes, there is an emotional component, like you put yellow lights and a little bit more comfortable. You dim the lights and whatever. You can create certain environments with it. But at the end of the day, it doesn't really matter how much energy these light bulbs use, because that's not what we're getting. We need light. We need to be able to write stuff down. We need to be able to see what's going on. So the core there is a benefit. So if you look at what delivers the benefit, the lights over there at the end of the room, are they benefiting anyone?
Less than these.
Hmm?
Less than these.
Less than this, right? And there's a light way over there. So those lights are not, there's nobody there to gain the benefit. So when we talk about the energy efficiency, and people talk about the usage of energy, that we need to use less energy, in most cases, it's not a matter of using less energy, it's a matter of wasting less energy. There's so much light you need to be able to write and read and feel comfortable. There's so much energy you need to use to provide cold air for yourself through air conditioning. There's limitation to that. And then on the broader perspective on the resources, there's so much water you can drink, there's so much food you can eat. We can eat a lot of food, obviously. But there's a limitation to that, right? So everything else is a waste. If there's nobody there to gain the benefit, if it doesn't deliver the benefit, then it's a waste. But we talked about the package. It's not always a clear-cut situation, right? So I'll give you an example. I've actually spent many years in Oklahoma. So on the countryside, young guys, they usually drive pickup trucks, and they don't consider little sedans as a manly vehicle. It's part of their identity to drive a pickup truck. So if they're buying groceries and delivering groceries on a half-a-ton pickup truck versus a small sedan, is it a waste or is it a use? And it is? How would you look at that?
I guess from a fuel efficiency standpoint, it's a waste,
Right.
but it's useful, because I guess everybody is going to make that trip to the grocery store, so maybe it is the use.
Right. And then there's an individual component, right? The benefit is very subjective matter. If that person feels great because they drive a pickup truck, whatever, sure, drive your pickup truck. Now, for that person specifically, that's part of their identity. They're going to use that resource. There is some value they give. Now, it's all iffy a little bit, right? Because, we're going to think about the fuel waste. But can that truck be more efficient? Sure. So if the truck is more efficient, then the maintenance is not jeopardized in any way, but you still do whatever you need to do, and then everything is fine. So that's a thinking process that I would like you to consider when we're talking about energy efficiency. Use versus waste, and focus on the benefit. How much energy do we need to use to gain the benefit that we would like to gain? So one of my favorite widgets, I guess, space heater, right? Is this a problem?
Yes.
Yes, it's a problem. Why is it a problem?
It's an extremely inefficient way to heat a space, especially if it's, for a bigger space.
Right? Dangerous, right?
Often people are using them in the summer because the air conditioning is so cold, they're cold, so they set that up in their office.
Yes.
Makes no sense.
So from, again, going back to the experience in Oklahoma, what I found out, we worked with many state agencies, been in hundreds of buildings, summer, 100 degrees outside, every building has space heaters. Because it's so cold, because air conditioning is blowing so much cold air, and people are cold, and they put space heaters on, right? But the question is, whose problem is this? Is it a person who is using it?
Facilities manager's problem.
Who's paying the bills?
Who is paying the bills? Facility manager? Because obviously those who pay the bills pay the cost twice for air conditioning and then for heating, right? And then the facility management, what would be their concern here?
They're not properly managing the building.
They're probably not managing building, right? Because there is a need for that, right? The person is cold. And so how would you solve this problem? You're sort of almost there.
I mean, it depends on what the root problem is. Are the control systems malfunctioning? Is the system oversized?
Right.
Is the person wearing shorts and a t-shirt? There's a lot of variables.
Exactly. So there is no one solution. It is individualistic in terms of how that specific person feels there, and it varies from person's weight, age, everything, all the components that you were mentioning. But the reason I'm bringing this up, because this is part of this whole energy efficiency conversation. Energy efficiency in buildings is very personal matter. It impacts our personal bubbles, comfort bubbles. You're going into your office, you have your cubicle, whatever space that you work in, you need that comfort there. And if somebody comes in here and starts messing with it, changing lights, changing temperatures, you're gonna try to do something about it, whether openly or not openly. I've seen the space heaters when people found out that we were surveying buildings, and put them into drawers and stuff, and we saw that stuff. And that's not good, because the facility management need to know that they have these fire hazard things hidden under the desk somewhere, right? But there is an underlying problem there that needs to be resolved. And if you don't resolve this problem, then you need to provide some sort of a solution for this stuff. So instead of maybe this type of space heater, you use like a radiator oil-based heater that is safer and more efficient than these guys. And there are some spaces where you cannot, like if it is a large space, for example, sometimes you have a desk of receptionists, for example. It's a huge open space. There are main doors coming in here, so they need that bubble. Otherwise, you cannot keep the whole space comfortable, right? So instead of trying to make the whole space comfortable, maybe you can make this space comfortable, because this is where the person is. This is where the benefit is needed. All right. So now, since we have these changes happening and we already scrapped all passive efficiency design, we have all this technology that we can build whatever buildings, there is some thinking gradually growing in terms of maybe we're not necessarily building these things right. And partially it's because of the cost of energy, partially it's because of the general sort of awareness about sustainability issues, air quality issues, and so on and so forth. So what gives us some opportunities is the technological development that we had over the last 10, 15 years. There are some interesting improvements. The whole energy efficiency field just exploded with technology, and we want to go through some of the core parts here. So if we take, for example, sensors. Sensors became cheaper and easier to deploy with advances in material science, with advances in computing. You are able to collect all sorts of data, whether it's through infrared, ultrasound, heat, whatever. And then you are able to collect all that data, little sub-meters like these, to actually work with all this. And then you can get all that data and actually manage it somehow, analyze it and understand what's going on in those buildings. So this proliferation of the technology and the dramatic drop in cost of these things made it possible to know a whole lot about the building. Now, I can tell you 5 years ago, and even a little bit further than that, 7, 8 years ago, when there were a bunch of companies coming out with all sorts of new widgets, they didn't necessarily know what to do with it. They would say, we can put this stuff and you can collect all this information and it will help you make better decisions. What decisions? And how we're going to use that stuff? Well, we'll get you the data, you make the decisions. So now things are getting a little bit connected, where people are starting to understand, okay, if we have these little sub-meters and then they collect the energy use on a socket level, on a circuit level, we can see how this specific space is doing. And we can see how this specific piece of equipment is doing. Piece of equipment, usually equipment doesn't fail like all of a sudden. There is a gradual change that happens. So you can track the changes and you can really pinpoint the problems with all these sensors. Now this became, so if you look, for example, at the building as an organism, right? We have sensors. We can sense temperature, we can sense humidity, we can sense changes in air quality, in changes of light. It's the same thing. So if you look at a building as an organism, this is a set of sensors that allows the building to know what's going on inside and outside. Now, the other important component is the nervous system, the brains of this organism, right? The building automation system. So the building automation system, I was driving here and thinking about this stuff. Until recently, the sort of the best state of technologies, I guess, in the controls industry was actually based on steam. You had systems, you had pipes running throughout the whole building, pushing steam to control louvers and to control valves and you had the building automation system that made that steam move in all sorts of directions. Obviously, the system leaked like there is no tomorrow, right? And then you had a bigger compressor there. That was always a solution. You just put a bigger compressor because you cannot find the leaks in a large building of the steam system. It's just impossible. There are still a whole bunch of buildings with that kind of system, with running steam. But there is a transition to digital platforms. And then people are gradually moving into that. And on a digital platform, it allows you to do more things. It allows you to deal with more data. And it also allows integration of different components. The building automation system, in most cases, managed just air conditioning, right? That was the sort of the common application of building automation system. What is changing is they're integrating lighting, not just on the whole floor level, but a little more granular. They're trying to integrate access controls. When you slide your car and you go into the building, can the building know that this is you and this is your office over there and this is where the comfort needs to be provided, that benefit that we talked about? Now there's a lot of talk about it, and if you go to some conference or you go to some trade show, there'll be some company that will say, yes, we can integrate all this stuff, piece of cake. You can integrate, but it is not piece of cake and it's not walk in the park. Things are gradually moving in that direction, but it's still a major challenge to integrate various subsystems within the building under one control. And then you have building integrated photovoltaics or on-site renewable energy, right? I'm sure you've seen buildings where it's not just a canopy, but it's actually integrated. It's part of the design where you have a solar system. People used to ask whether you can put a wind tower on the roof. People still ask those questions. There are vertical wind towers, maybe at some point, but usually it doesn't really make sense. But you can put, obviously, on the grounds, if you are a campus like this, you can put a small wind application. And these things now can be connected. So you create, in a sense, like a microgrid, using the popular term these days. So this becomes your little system, where the energy from the wind, energy from the solar, whatever the backup generator that might exist there, and from the grid, they all are managed so that your building always has what it needs. Right? All right. The other important innovation that I would like to mention is LED lighting. I'll tell you why. I think the LED lighting is just as revolutionary as probably the original light bulb itself. What it does, if you look at this light bulb, there was, until recently, this was sort of a typical shape of LED light bulb. Some looked even weirder than that, with little pointy little LEDs coming out, and people had real objections about using those LEDs. Also until recently, you had mostly either bluish, whitish kind of a color. So you didn't have a full range of colors that people can use so that they can mimic the yellow light that we got used to over 100 years with incandescent bulb, mimic it and then still feel comfortable that, yes, I'm getting the same quality light. So people created a bulb that looks like a regular light bulb. There is really no need for this for the purpose of generating light. This is simply a psychological tool. Because people had objections to the shape of the light bulb, they had objections to these weird looks. So people went out of the way to design this light bulb to make it look like a normal light bulb. And then you have this type of advances that I'm sure you've seen around over the last couple of years. This is also an LED light bulb. First time I saw it, I thought it was just an incandescent, like fancy looking incandescent bulb, but it is an LED bulb. These are the advances in technology. The reason I'm saying that this is revolutionary technology is because LED is not really, in my understanding, it's not really lighting. It's electronics, right? It's a little component that emits light. It's a diode, right? So what it does, as you can see from LED screens, for example, right? Once the full range of colors became available, you were able to have large LED TVs. You can have the billboards, LED billboards. So you see the full quality video on the LED screen, right? So that's not light bulb. It's a different technology. All this stuff here, it assumes a central location for the light bulb. Just like starting from a candle, you sit at a table, like before the light bulb, there are candles located, and then you have light emitting in all the directions. Light bulb took its place. It became that candle that emits light in all directions. So we needed psychologically to have that light in a central location. This is a little bit distributed as we start moving in the big places. But still, the main concept here is that that fixture emits lights in all directions. Now what LED does, it allows to create surfaces. You can have the whole surface emitting soft light and still using a whole lot less energy. So the architects first probably will start experimenting with those things. Saying, okay, in this room, instead of having these light fixtures, can I have ceiling emitting soft light? So that you don't have shades, you don't have issues of glare. You just have ambient light. Some high quality ambient light that allows you to do things, whether write or read or whatever. And the same goes for other surfaces. And then the advances in material sciences are kind of leading there that per lumen of energy, per lumen of light that you need to get for benefit, the energy use is going dramatically down compared to incandescent. So these are components that enable the building, when we talked about the benefit, to provide you with the benefit of light at a fraction of the energy use. But it challenges the thinking process. You walk in, is there a light bulb? How long, all these little jokes that used to exist, how many people, how many engineers or architects or doctors, whatever it takes to change the light bulb, that will go away, because then you will not have light bulbs. You will have surface emitting light. So we took all these different components of the building, of different advances in technology. Now we're going to look at the entire building. So please feel free to interrupt as we go through. All right, we're going to look at building as a system. Here's my question to you. What's in the system? We're talking about the building as a system.
Water systems?
Water systems, okay.
I mean, depending upon what kind of building it is, it could have, compressed air system.
Air conditioning, other examples? Sewer. Roof, an envelope, right? That's part of the system. What else? People. People are an important part of the system. Because at the end of the day, this whole building needs to work for people. And amazingly, I've been working in energy efficiency for 12 years. People forget about that part. They forget that what the work that they're trying to do, the efficiencies that they're trying to achieve, they're all for people in those buildings, whether they live in those buildings or work in those buildings. If it doesn't make sense for them, then it doesn't make sense at all. And there's a joke that I heard many years ago, where they say that architects and engineers design this great building, super duper great building, and then people came in and messed everything up. And this is an unfortunate truth, of how the projects are done. When you take a whole building and you say, okay, we need to make it more efficient, what does it mean? We're going to change the temperatures. Well, what if people complain? Well, we'll tell them it's a policy, so you cannot complain. And that's a solution. People use that all the time. And they assume that it's going to work. But then what? You get space heaters. Because it doesn't. Right? But what else goes into this? You got a little bit of renewable energy going here. What about the landscape around? Is that part of the system? Because that's going to impact how you use energy, right? If your building is right next to a huge parking lot, and in the heat of the summer, right, that parking lot will absorb all that heat, and it's going to be emitting heat for many hours after the sunset, and then your building will have to deal with it. Quite often the air conditioning goes on top of the buildings on a black tar roof, so if you measure the temperature where the equipment is, you can be like 150 degrees. And your little piece of equipment there trying to, especially when they put like a heat pump, they're trying to fight that 150 degrees air. And that's just not sensible, I think.
And the AC is getting out here as well.
Right, which adds to the overall problem, right? So you need to, if you look at the building as a system, you go sort of up. You start from people who occupy and manage the building. You actually take the physical components of the building, the structure itself. We talked about passive efficiencies. So these are the bones of the building, the walls, the roof, the foundation. You take the equipment that manages the building, plug loads that can be unplugged and the building can still survive, right? But then you have your AC and hot water and all those systems, and then you expand out to the environment around the building. Now sometimes you don't have a choice. If you're building in the middle of Manhattan, for example, you don't have a choice. This is your box, this is what you're going to build. You have choices inside the building, maybe you have choices about the envelope, but you don't have a choice around the environment. So there's a building across from you that is facing just right so that the light, at the sunset reflects and it goes into your building. You'll have to deal with it one way or another. You just don't have an option. All right. So the other component of the system is the cost of energy. How you pay for energy is going to impact your decisions, right? When you're going to run the building. Obviously, a college building, you're not going to run it at night just because the energy is cheap. You're still going to have classes during the daytime, right? That's a benefit. That's what we see. So can we get that benefit in a more efficient way or less costly way? So the financial component is just as important as a technological component. It's just as important as people component, because the decisions at the end of the day quite often are made by people on the senior level, and there's a financial decision. It's not a technical decision, it's a financial decision. I'm going to put this much money in and it's going to generate this type of savings, and that's it. Does it work? No, it doesn't. Or yes, it does. Here's a little example from a project I've worked on. Many of these examples coming from, I just moved about a little year ago from Oklahoma, so these are examples from Oklahoma. So you see here, these are different fees of electric bill of a portfolio of facilities. And here's a franchise fee. This green is a demand charge, so it's a little bit over here, and when it goes up over summer month, obviously air conditioning kicks in, so demand went up, and the rate in summer is a little bit higher, so the cost of demand went up over here. The blue is a charge, electricity charge, per kilowatt hour charge. And this little red thing here is what they call fuel adjustment fee. So fuel, this is in the regulated market. So in the regulated market, the utility, and to some extent things are valid in deregulated markets as well. But there in Oklahoma, as an example, utility changing kilowatt hour rate is very difficult. They have to run certain applications, make the case, there are a whole bunch of hearings. It's a complex process, very difficult. So they really want to make it that yes, we have all the information in place, we have all the good reasons to change that rate. Now this fee over here, the fuel adjustment fee, was specifically designed to pass down the cost, the fluctuations in cost of the fuel. It was originally set up during the high gas prices, natural gas prices, but at that time, Oklahoma's natural gas consumption for the power generation was relatively small. But as it was going up, then what happened is that the natural price for natural gas went down, but the fee still remained in place. So what happened over here? Any ideas?
Splitting generation from delivery.
Could be, right? But what actually happened here is that they flipped the fees. So what they did, they reduced kilowatt hour charge, which is okay. You don't have to go through a complex process for a reduction. The increase is what's challenging. And then they increased the fuel adjustment fee. So they pushed more of the cost into that fuel adjustment fee. Now overall experience, I mean, it's a normal curve, so people didn't see dramatic change in the energy cost. Overall bill stayed the same. Very consistent from summer to summer, not a big deal. But remember, this is fixed, the rate, and this is not fixed. Now you have a big chunk of your bill that you have no control over the rate. That's a risk. That's a tremendous financial risk. And I've been to work with one building which is totally electric, medical buildings. They have blood there, blood problems, so they have refrigeration. So they're going to run the electricity one way or another, regardless, because that's the line of work. 40% of their cost of electricity was in that fuel adjustment fee. That's a tremendous risk, financial risk. It doesn't necessarily go into the consideration as far as energy efficiency or whatnot. That's not something that pops up right away. Nothing changed in the building. It's still the same building, equipment is still the same, things are happening the same way. But the cost of energy and how it's charged changed. Now that's going to impact the decisions, how that should impact. This knowledge should be in the hands of building owners so that they make better decisions at what equipment goes there, how they control their facility, so that they minimize, they cannot eliminate it, but they can minimize this risk over here. So another part of the bigger system. All right. I want to go back to our favorite image over here. So I'm going to put it sort of in the broader perspective. Now, this is where most of the other seminar sessions were covering. You have the full chain of power generation, and these are all obviously in a transmission. This is a complex field. It needs to be managed. There are all sorts of national security issues, global environmental issues, whatever. There are lots of components. But at the end of the day, this whole system exists for this. The buildings at the end of that food chain, whether it's manufacturing, commercial, or public building, it doesn't matter. It's for this, right? We don't consume electricity. We consume those benefits. We need electricity to run equipment. We need electricity for life, for comfort. So energy efficiency, from this perspective, has to play a major role in overall energy system. Because how you use energy on this end, these guys right now try to react to this. And with some efficiency programs, they try to mitigate some challenges. You have these demand management programs where they give you some money if you cut your power use by so many kilowatts at the peak of the hour. Or you turn your power off and you run off the generator within those hours. It's just so that they can manage, the utilities can manage this component and this component, the generation. Right? I've seen in Oklahoma, I've seen these newly built power plant with 4 generators, 2 very large ones and 2 80 megawatt generators. And one of those 80 megawatt generator was peak generation. It idled the whole year and actually worked full force few hours a year. So you maintain this whole infrastructure to satisfy that peak. Because if you don't, you're gonna have a blackout, right? But this is where that peak consumption happens. When we go in and it's 100 degrees outside, all the AC kicks in, and people turn on TVs and microwaves and all that stuff, and you have the peak demand, and then they kick in the 80 megawatt generator to make that happen. And if you're able to manage this, then you're going to have that impact on this other end. It's going to impact the overall infrastructure. Now, all these developments that I was talking about and the renewable energy that's getting integrated into the buildings pushes the buildings into the realm of net zero buildings, for example. The buildings that over the span of the year generate as much energy as they consume. Now, that impacts of how they take the energy from here, right? And there are buildings that are ready to be off-grid, with energy storage dramatically improving and lowering in cost. You can come to the point where you can cut the cord. It's not everywhere. I've seen farmers doing that. They put a little wind tower, put a little solar panel, storage, a little backup generator, and cut the cord. They don't need utility.
Two quick questions, if I may.
Sure.
Number one, are the efficiencies as bad as what you're showing over here? And second question is, for those people that are able to cut the cord, are their efficiencies better?
So on the coal-fired power plant, this is an example of coal-fired power plant. So these are typical numbers for coal-fired power plants. Natural gas generators are more efficient. I don't know their efficiency numbers, but they're much more efficient. The challenge with these guys, obviously, they run 24/7, and you always have to run them. There's no way to ramp up or ramp down. Natural gas allows that so that it adds to overall efficiency of the system. An interesting side effect that happened in the state of Colorado when they put a whole bunch of wind and they thought they're going to lower their emissions. The emissions actually went up because the base load was provided by coal. So what they try to do, they try to ramp up and ramp down these things, which when you do that, you have the puff of emissions coming out. So their emissions went up. So it is an inefficient system. I think coal-fired power plants, they serve their purpose, but we have better options. The grid is actually relatively efficient from my understanding, especially some of the changes to like high voltage lines, the transition to DC. I wasn't familiar with the technology, but as I started digging in, I saw that it's a more efficient system. And how we manage is becoming more efficient. We talk about smart grid, right? So there's ability to manage the flow of energy a little bit better. The other part of your question, the other question about the people who go off-grid, the challenge with going off-grid has two components, and those two components need to be satisfied. One is the power generation, right? Do you have, the solar panels are efficient enough in terms of how much energy they generate? Is the wind tower efficient enough, how much energy they actually convert. And then there's a cost component to that. But the other side is efficiency. How much energy do you need? Right? So if you look at the LED lighting, if you look at the Energy Star appliances, if you look at the smart building, then your needs go down. I met recently an architect. She's building it's a high-end condo in a townhouse in Manhattan. Its peak demand will be less than a good hair dryer. So if you turn the hair dryer on, you're going to double the need of the building. So that they took extra effort to build first passive efficiencies, so the building itself doesn't need as much. It has like if you look at the Adobe house, has a good thermal mass. So it takes a while for the house to heat up, and it takes a while for it to cool off. So there's that lag that helps you maintain it. So using whatever adequate techniques for the specific climate, you do that first. And then you lower the technical component, the LED light bulbs, air conditioning system, and whatnot. And then your need is minimal, and then you put solar panels on top, and wind tower, and you're ready. You need storage. Storage was a big challenge until recently. It still is. It's becoming much better. But putting large lead-acid batteries that you need to service, that you need to take care of, you need to have a special place for that. There are all sorts of rules related to that. That was a major problem. Now things are improving in that direction, so that you can build a pretty sleek, quiet system that does not require much maintenance.
Looks like the worst, by far the worst inefficient component is the light bulb itself, which gets back to what you were saying a few slides ago.
Right, the incandescent bulb. Now, I'm not saying that incandescent bulb is bad. Again, we're talking about the benefits, right? It has its own places, I'm sure. It just needs to be there where it needs to be. If we need light, we need light. We don't need 97% of the energy that goes towards the heat for that. We need light. If we need heat, maybe that's not the best way to heat, but I'll give you a very interesting example. So again, in Oklahoma, where they get ice storms. At the peak, when everybody was so excited, people came up with the LED traffic lights. So they put a whole bunch of LED traffic lights. First ice storm. Ice doesn't melt because LEDs don't generate heat. So traffic lights are just covered with ice and nothing is happening. So well, that doesn't work. So they changed back to incandescent bulbs because there is a specific need for that. Maybe you can figure out some other way to heat so that you can get rid of that ice. If there is a different solution, then you have a different solution. But until then, you have to have incandescent bulb because you have an obvious problem there. So that's I think the thinking process I need to go.
If I may ask just one
Sure.
other quick question. Are there any studies, is there any information or not regarding the health benefits or risk, either way, of LED lighting versus incandescent? Is one better than the other? We just don't know. I haven't read any studies that compare those two. What I can tell you, when there were studies that were researching fluorescent bulbs, right? So incandescent bulb and LED bulb is something they call solid state light. So there's just light coming in. Fluorescent bulbs, they're actually always going on and off cycle. So if you take, I had a friend who had model airplanes, so he had the little thing to measure how fast the propeller is rotating. So we aimed at the light bulb to see what's going on, and these guys, the newer ones, they flash 3,600 times per minute. For most people, it's not a problem, but you may the respectable older generation may remember the 80s when people had headaches from the fluorescent bulbs because they were like at 1800 per minute. So the eye still notices. We still notice those fluctuations. It's just we're okay, we don't have migraines and whatnot, so it doesn't necessarily impact us immediately. Long term, maybe. But the people who do have migraines, they're very sensitive to fluorescent lights. So when you move to the LED light, that is a solid state light, you remove the underlying cause for the headache. So that component is definitely there. In terms of quality of light, LED allows coming closer to the daylight. Now we're used to yellow light, so a lot of people would say, you know, I want my old incandescent bulb because of the color. That's not necessarily the best light for the eyes. It's just something that we psychologically comfortable with. Now LEDs can, you can match the color with the color of the sun, so you will have good quality light, which gives you good, what they call color rendition. You may come across, there was a challenge in California with one food chain that people were not buying meat. It looked brown. And so they changed the lighting, they put the day lighting, they put LEDs, meat became red, and people started buying meat. Now when I read that, I got concerned, because you can manipulate people very easily. Right? It's a perception. I can make that brown meat look red if I put the red color into that. So these are dangerous tools, these LED lightings. We need to be aware of those things. All right. So the last thing I want to leave you with, you know, buildings are important parts of the energy system. People are important parts of the energy system. Smarter approach to building design is combining old knowledge with technological innovations. Those passive efficiencies, what was built over thousands of years. Broad organizational and societal change in how we understand energy and interact with energy. You know, we had a history with energy already, over 100 years. Their habits developed. Those things will need to change. If we are still getting the benefits, but we're just wasting less energy to get those benefits. Learn, act, and learn some more, because this field is just advancing so fast. It's almost impossible, you know, unless you read, unless you visit projects and whatnot, it's very hard to stay up to date on the technological advancements. And you know, where to go from here, that's pretty much your choice. The information is there, you decide. All right?
Do you feel that these ideas and techniques are making their way into residential at this time, or will it ever happen, or, you know, because I live in a house that was built for electric heating. And we have the air conditioner, we have two zones, one's in the attic, it's really hot. And there's not much you can do to change it once it's built like that. And I don't think anything's changing in residential construction. Of course, for apartments and condos where they have one single owner, they can, you know, they can do that. But if you're buying an individual house, it's, you know, they throw whatever in there and then you got to pay.
Obviously, when you're purchasing, you're making lots of decisions, not just the efficiency component, right, in terms of whether to buy that specific house or not to buy that specific house. When you raise those questions about the energy performance, if a lot of people raise those questions, then the builders will react. Some builders build Energy Star rated homes, for example. Not because they just feel good about it, some do, but because people ask for it and they're willing to pay sometimes extra, or sometimes that's a way for them to differentiate. Now, if you take an existing home, you can do things. You're limited in how much you can do. If you're planning to be there for a while, if you're not moving, then it allows you to do some improvements that may not have immediate payback, that may gradually improve comfort for you. Your attic, if you look at the house, you go back home, when it's cool, you know, you put your hand, make it a little bit wet, put it next to the outlet, especially on the internal walls. And you'll feel the air blow. The air comes because the walls are hollow. They're connected usually to the attic or to the crawl space. There's no seal there. So in a sense, the space inside the wall is connected to the outside. So you get the air moving in. So you have all these losses. But at the same time, you can seal up your house. This is when people run into problems that if you seal up the house, you trap all the off-gassing because there's no fresh air coming in. The buildings, the houses are designed to leak because this is how you get your fresh air. Of all the homes that I inspected, I found one is because it was designed by an engineer or himself, he put a fresh air intake system. Everybody else, the only way you get your fresh air is through the hose. So there are things you can improve, and I tell you, if you go to the Energy Star's website and you go to the home section, there will be lots of interesting recommendations there that you can do, little things that you can do.
In the interest of time, because we have a class,
Sure.
Alexei or Mike is going to make a presentation.
We'd just like one more round of applause for Temur real quick. Institute, we'd just like to say thank you. This is a small gift as a token of our gratitude.
Thank you.
We have these distinguished lecture series every other Wednesday, 4:30 in this room. This was really a great presentation, and thank you for your time.
Appreciate it. Thank you. Thank you again.